Okay, in this slide we explain about the turbine cascade correlation that obtained by Ainley and also Mathieson in 1951. So Ainley and Mathieson introduced a method to investigate the performance of an axial flow turbine that use impulse blades. So they conduct investigation about pressure loss due to profile loss for impulse turbine blade. So the figure shows the arrangement of impulse blade on the rotor and also stator for impulse turbine. And the second figure shows the arrangement of the impulse blades on rotor and also stator, or sometimes we call nozzle, into the view, two-dimension view. So we have, for the first row, we have what I call the impulse blade arrangement on the rotor, and the second row represent the arrangement of impulse blades on the rotor, or sometimes we call nozzles. Okay, condition number one represent the inlet of the of the cascade blade or of the rotor, and number two represent the condition at the outlet of the rotor. So in terms of result that obtained by Ainley and also Mathieson, for this case, for impulse blades, they obtain profile loss coefficient of turbine nozzle or stator and impulse blade at zero incident angle, I equal to 0. And this result is specific for blade profile, where T over L equal to 0.2 and flow condition with Reynolds number equal to 20,000 and Mach number below than 0.6. So the information that we will obtain from this result, actually the total pressure loss correlation based on profile losses. So we have the first result that's shown by the graph is the result in terms of profile loss coefficient YP, represented by symbol YP for the turbine, for impulse turbine, versus S over L, and this data or this result for nozzle blade or stator, where alpha 1 inlet flow angle equal to 0. So in this graph we have numbers of curve that represent the result for different value of alpha 2 outlet flow angle, start from 40 degree up to 80 degree. So in case you need to determine what I call the data for alpha 2 between 70 degree and 80 degree, so you need to make your own graph by using interpolation method. So you need to make estimation curve to obtain the specific data by using the graph. And this figure shows the what I call the condition of flow at the inlet and also at the outlet of the nozzle blade or stator. So the green line represent the chord line. So we have alpha 1 equal to 0 because the inlet flow direction is parallel to the chord line. So we'll get, for this condition, for this result, for the first graph, alpha 1 equal to 0. However, in terms of value of outlet flow angle, for this case alpha 2 is not equal to 0. For the second graph, the result that obtained by Ainley and Mathieson represent the correlation in terms of profile loss coefficient YP for impulse blade versus S over L for impulse blade rotor, where alpha 1 inlet flow angle equal to alpha 2 outlet flow angle. And we have numbers of curve represent the curve for different value of alpha 2 outlet flow angle. Okay, this schematic diagram shows the condition of flow, inlet flow and also outlet flow angle for impulse blade or rotor. So we have chord line. So we have the angle of alpha 1 which is not equal to 0, and also alpha 2 outlet flow angle also not equal to 0. So for this case, the value of alpha 1 must be equal to alpha 2. Okay, so for example, if you need to determine profile loss coefficient for impulse blade, let's say you need to determine profile loss or total pressure loss for the stator or for the nozzle. Let's say the value of S over L equal to 1.0 and the outlet flow angle alpha 2 equal to 60 degree. So from this value, because you need to determine the profile loss coefficient for the stator, you need to refer to the first graph, the graph that refers to the nozzle blade, alpha 1 equal to 0. Okay, so draw the vertical line at S over L 1.0, intersect with what we call the curve for alpha 2 60 degree. So we will obtain the value of profile loss coefficient YP equal to 0.028. In case you need to determine the profile loss coefficient YP at the rotor, so you need to refer to the second graph. So the graph for impulse blade rotor, where alpha 1 equal to alpha 2. Let's say the value of S over L equal to 0.8, alpha 2 equal to 60. So draw the vertical line at the value S over L equal to 0.8, intersect with alpha 2 curve equal to 60 degree. So you will obtain the value for profile loss coefficient YP for the rotor, where the value around 0.112. So that's how you can use the graph for the stator and also rotor for the impulse blade in order to determine the profile loss coefficient. Okay, in terms of turbine cascade correlation, they are obtained by Ainley and also Mathieson in 1951. Ainley and Mathieson also introduced a method to estimate the performance of an axial flow turbine that use reaction blades. So where they conduct investigation about pressure loss due to profile loss for reaction turbine blades. Okay, the figures shows the arrangement of reaction blade on rotors and also stators for reaction blade, and the second figure shows the arrangement of the reaction blade in two-dimensional view, where we have the arrangement of reaction blade on the rotor and also on the stator or nozzle. Okay, state number 1 represent the inlet condition of the rotor, and state number 2 represent the condition at the outlet of the rotor. So in terms of result, Ainley and Mathieson also obtain the variation of profile loss with incident for typical reaction turbine blade. So this is the result that obtained by Ainley and also Mathieson for the reaction blades. So we have the correlation between profile loss ratio YP divided by YPI equal to 0, and also incident angle ratio I divided by IS, where IS stand for stalling incident angle. Okay, so from the graph, if we know the incident angle ratio I over IS value, so we can determine the profile loss ratio for the reaction blade. So if somebody asks you about what is the stall point in the graph, so in order to determine the point, so the incident angle must be equal to stalling incident angle, where in terms of ratio IS over IS equal to 1.0. So this is the stall point in terms of incident angle ratio. So from the point, we also can determine the profile loss ratio, where we just draw the vertical line, intersect with the curve of the profile loss coefficient, and the value of profile loss ratio will be around 2.1. So from profile loss ratio value, Also, we can determine the value of YP, which is represent the profile loss coefficient for the reaction blade. In terms of formula, YP equal to the pressure difference in terms of stagnation pressure at the inlet minus stagnation pressure at the outlet divided by stagnation pressure at the outlet minus the static pressure at the outlet. So the YP value in the graph actually is taken at the same S over L ratio and also alpha 2 outlet flow angle. And YP I for I equal to 0 is referred as the profile loss coefficient for the reaction blade when incident angle equal to 0. Okay, different from impulse turbine or impulse blade, for reaction blade there is no YPI equal to 0 graph. So that's why we consider the blade, reaction blade, as the other types of blading intermediate. They are intermediate between nozzle blades and also impulse blade. YP at I equal to 0. So we need to use the data that we obtain for impulse blade in order to obtain YPI equal to 0 for the reaction blades. So the figure shows the condition of the flow for the reaction blade, where the green line represent the chord line. So we have inlet flow condition with alpha 1 angle, where alpha 1 angle is not equal to 0. And we have the condition at the outlet, where alpha 2 outlet flow angle also is not equal to 0. For the reaction blade, alpha 1 is not equal to alpha 2. So because we don't have specific graph for reaction blade in order to determine YPI equal to 0, so we need to use this specific YPI equal to 0, YPI equal to 0 for the reaction blade. So we can use this equation where YPI equal to 0 equal to YP alpha 1 equal to 0 plus alpha 1 divided by alpha 2 square multiplied by YP alpha 1 equal to alpha 2 minus YP alpha 1 equal to 0 multiplied by T over L divided by 0.2 power of alpha 1 divided by alpha 2. So this equation already includes a correction for the effect of thickness chord ratio, and the equation only valid for T over L value between 0.15 up to 0.25. So because the reaction blade we consider as the other types of blading intermediate between nozzle blade and also impulse blade when incident angle equal to 0, so the value of YP alpha 1 equal to 0 in the equation, we need to refer to the data they obtained for YP alpha 1 equal to 0 for the impulse blade, and we need to refer to the figures, the graph for nozzle blade for the impulse blade when alpha 1 equal to 0. Okay, and then we can substitute the value into the equation for YPI equal to 0 for the reaction blade. Okay, similarly with the value for YP alpha 1 equal to alpha 2 in the equation, so this value also we need to refer the value for YP alpha 1 equal to alpha 2 refer to the result they obtained for impulse blade. So we need to refer to the second graph for the impulse blade where alpha 1 equal to alpha 2. So from the graph we can determine YP alpha 1 equal to alpha 2 and then substitute into the equation for YPI equal to 0 for the reaction blade. Okay. Example 3.10. In an investigation of cascade blades, a gas is flowed through a reaction turbine cascade blade with inlet and outlet flow angle of 20 degree and 70 degree respectively. The cascade blade arrangement has a spacing distance between blade equal to 8 cm. The blade profile has a blade thickness and chord length of 2 cm and 10 cm respectively. The arrangement is set at incident angle of 5 degree, with stalling occur when the incident angle at 10 degree. By referring to the figures provided, determine the profile loss coefficient for the cascade blade. Okay, solution for example 3.10. So data given. So from the question, we know that the question involves with reaction blades, where alpha 1 equal to 20 degree, alpha 2 equal to 70 degree, thus alpha 1 is not equal to alpha 2. So we consider the problem involved with reaction blades. So data given, I equal to 5 degree, IS equal to 10 degree, S over L equal to 0.8, T over L equal to 0.2. So S over L and also T over L we can calculate by referring to data given in the question. And we need to determine the YP value for the problems. So from graph alpha 1 equal to 0 for S over L equal to 0.8 and alpha 2 equal to 70 degree. So from the graph, so we can obtain the value of YP when alpha 1 equal to 0, which is equal to 0.04. From graph alpha 1 equal to alpha 2 for S over L equal to 0.8 and alpha 2 equal to 70 degree. So we can obtain the value of YP when alpha 1 equal to alpha 2, which is equal to 0.065. So calculate the incident angle ratio. So we will get I over IS equal to 0.5. So from the profile loss ratio graph for the reaction blade, so we can determine the value of profile loss ratio YP over YPI equal to 0 equal to 1.2. So we obtain the value from the graph. Determine the pressure loss coefficient at 0 incident angle by using below equation. So this equation specific for the reaction blade. From calculated data, where YP alpha 1 equal to 0 equal to 0.04 and YP alpha 1 equal to alpha 2 equal to 0.065, and in terms of alpha 1 divided by alpha 2, we can obtain equal to 0.2857 because we already know the value of alpha 1 and also alpha 2, where alpha 1 equal to 20 degree, alpha 2 equal to 70 degree. T over L equal to 0.2. So substitute all the values into the equation of pressure loss coefficient at I equal to 0. Thus we will obtain YP I equal to 0 for the reaction blade equal to 0.0502. Substitute the value of YP I equal to 0, YP I equal to 0 into profile loss ratio to obtain YP value. So from the graph of the profile loss ratio for the reaction blade, we already got the value where YP divided by YPI equal to 0 equal to 1.2. Substitute the value of YPI equal to 0 equal to 0.0502. So we will get the profile loss coefficient YP equal to 1.2 multiplied by 0.0502 equal to 0.0602. This is the value of profile loss coefficient for the reaction blade in the question, in the example 3.10. Okay, for turbine cascade correlations that are introduced by Ainley and also Mathieson, there are a few other correlation that are introduced by Ainley and also Mathieson based on different type of losses. So previously, the correlation that we already discussed, the total pressure loss correlation that introduced by Ainley and Mathieson actually based on the profile losses. However, Ainley and also Mathieson also introduced the correlation of total pressure loss correlation based on the secondary losses. So from the correlation we will get the pressure loss due to secondary loss for the turbine. Okay, so secondary loss coefficient that introduced that proposed by Ainley and also Mathieson for the turbine, that represented by YS symbol, where YS equal to CDS multiplied by cos alpha 2 square divided by S over L cos alpha m cubic equal to lambda multiplied by CL divided by S over L square multiplied by cos alpha 2 square divided by cos alpha m cubic equal to lambda Z. CDS is stand for drag coefficient due to secondary losses. This term we already discussed in previous lecture or in previous chapters, where CDS equal to lambda CL lift coefficient square divided by S over L, where the lambda value represent a function of the flow acceleration through the blade rolls. So if you face the problem involved with secondary loss coefficient, normally the value of lambda will be given, and Z value is the blade loading coefficient, and normally the value of Z also normally given. Okay, the last correlation that introduced by Ainley and also Mathieson for turbine cascade correlation is the correlation involved with total pressure loss due to or based on the tip clearance loss or fluid leakage loss. So from the correlation we will obtain the pressure loss due to tip clearance loss or fluid leakage loss. So Ainley and Mathieson introduced the equation for the tip clearance loss coefficient, where represented by YK symbols, where YK equal to B multiplied by L over H multiplied by K over L power of 0.78 multiplied by Z, where L is the chord length, H is for the blade height, and Z is for the blade loading coefficient, and K symbol represent the clearance gap as shown in the figure, and the clearance gaps also same as the tip clearance distance. B value is depend on the type of turbine blade tips. There are two types of blade tips. First we have the plain tips as shown in the figure, and the second one we have the shrouded tips, and the value of B depend on this type of tips. So for plain tips clearance, the value of B equal to 0.5, and for the shrouded tips clearance, the value of B equal to 0.25. Okay, in this slide I will summarize the content of chapter number 3 for cascade blade performance. Okay, so in order to determine turbo machine performance, so we need to make estimation or prediction. So in order to make estimation or prediction, we need to conduct cascade blade investigation, as we have learned in chapter number 3, where we already learned about the blade profile, the effect of blade profile, the effect of inlet flow condition in terms of inlet flow vector, and also angle of attack to the efficiency of the cascade blade. And also we already learned the effect of lift coefficient or lift force, and also drag coefficient or drag force, where we need to make sure that the value of L is maximum and the value of D is at minimum condition. So if the value of drag coefficient or drag force increase very high, so it will promote the separation flow, where we have learned in chapter number 3, when the condition have more separation flow, the total pressure loss in terms of delta P0 will increase, and this separation flow also promote various phenomena in the turbo machine, such as stalling phenomena, surging, and also choking phenomena. And all these parameter, all these conditions will affect the efficiency, where this condition will reduce the efficiency of the turbo machine, including the compressor and also turbine. So we need to know the optimum value of efficiency and also the maximum value of efficiency for certain blade profile. So that's why we need to study about how to minimize the losses. So in order to obtain the optimum value of efficiency and also minimize the losses, so that's why we study about the investigation involved with compressor and also investigation involved with turbine. So for the compressor, we already learned about the investigation that conducted by Howell, and Howell studied a lot of parameters that affect the efficiency of the compressor and also the parameter that affect the amount or the value of the losses for the compressor. However, for the turbine investigation that conducted by Ainley and also Mathieson, Ainley and also Mathieson what we call study numbers of parameters that affect the performance of the turbine and also the parameter that affect the value of losses in the turbine. So from Cascade investigation, we can know the relation between the performance parameters and also the blade profile parameters. Okay, in order to test your understanding for part number 7, chapter number 3, answer the question below. What is the minimum profile loss coefficient value for a turbine reaction blade? Question number 2, what is the value of YP alpha 1 equal to 0 represent for? Okay, you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue also given in the link. Okay, so you have to answer the question. Okay, that's all for part number 7, chapter number 3. Assalamualaikum.